Today we are visited by Professor Mike Faulkner from Victoria University in Melbourne, Australia. Mike is a professor there in telecommunications, and he has been there for around 15 years, and during those 15 years he has, among other things, built up a well-known research center called the Telecommunications, the Center for Telecommunication and Microelectronics, CTME. Mike is very well known internationally in the research. He has published well over 100 scientific publications, all recognizing a lot of citations. He has also been responsible for educating more than 20 PhDs and, as I said, build up these research activities in Melbourne. He has also a lot of experience from collaboration with industry, among those industries also in Sweden. So we are very happy to have you here, Mike, and looking forward to your talk. Let's welcome him with a big hand.
Okay, thank you very much. And yeah, thanks for coming. All right, so yes, I've been at Victoria University actually nearly 40 years. A long time. And yeah, I've been in the mobile field for almost 30 years, I guess, since the GSM days. In fact, I got into the mobile field by coming to Lund here and working with some of the guys on linearizing power amplifiers, which is my first project. Okay, so today we move into millimeter waves, which for some people, like many of the telecom people, is quite sort of a new area. Wireless LAN people have been there for a little bit longer. And of course, there's specialized usage of the band also. So I guess you've all seen this slide before because it's an Ericsson slide, which basically says 60% growth in mobile data traffic annual growth, and that's basically the business case for everything that follows, pretty much. Clearly, they think, and I guess you'd have to be quite brave to think the other way, that it's going to continue. So in order to allow it to continue, we need to move to a new generation of products, 5G, which of course I guess has some commercial benefits for everybody. The 5G will also bring in some new features, of course, like Internet of Things, virtualization, and you know, vehicle to vehicle and stuff like that. But my feeling is that in the past I've had foot in both camps. There's one camp which is the cellular camp, and the other camp is the wireless LAN camp, right? And they're all fighting for each other's territory. So I don't know whether V2V will in fact be a cellular thing. It could very well be a wireless LAN type thing. We'll see. Okay, so I'll just introduce a little bit about 5G, and then the need for channel models, and then the measurements that we've done here at Victoria University. Okay. So this is the Moore's law of wireless comms. It just keeps on going. Basically, every time a new bubble comes here, I have to take an old bubble off there. Okay, so it actually goes right on back down to GSM, but that's all been taken away. You can see that the data rate's going up almost 10 times every 5 years. Or at least that's what it's projected to be. Whether we actually get to 30 gigabits per second, I don't know, but they'll probably get close. You can see that 5G comes in here. It's going to start somewhere around about 2020. brings in all these new features, or some of these new features, of which millimeter wave, I think, is probably the most novel, I think, for the wireless, at least for the cellular community. 5G is sort of going to see a little bit of a divergence in technologies, a little bit more. On the left-hand side, you can see this is the more of the same, right? Ultra-fast devices. It's what you have in your pocket now. It's going to go higher and higher data rates, etc., and you'll have more and more things you can do on it. But it will also put a lot more emphasis on this area here, which is smart sensors and narrowband IoT, where the low power consumption of the sensor is clearly one of the big issues to address. So 5G, of course, has got to last until 2030, in which case we're expecting the capacity to be 1,000 times up, at least 10 times more increase in connectivity, more items, and then energy per bit is coming down by 1,000. So basically the energy is staying the same. So we're not going to use any more power to run our base stations and things. So that's the hope, at least. And throughput and reliability. Now, reliability, I think, is the tough one, because that basically is saying 100 megabits per second at the cell edge, which is where it's all the most difficult to achieve. You can always get close to the base station and get your high throughput, but at the cell edge it's a bit more tough. So millimeter waves will play an important part, and people are beginning to ask these two questions, you know, what cost and what reliability. and the operators in particular are asking that question because they know that the spectrum's going to become available, and eventually they're going to have to bid for it. And so when they start bidding for it, they've got to know really how good it's going to be, and how much infrastructure they have to put into it to make it acceptable. So it's a trade-off between cost of spectrum and cost of infrastructure, and that's what they need to know. So there is a need, therefore, for as far as millimeter waves, to know, you know, just how they perform in different environments. And of course, in Australia, our local operator, Telstra, is interested in how it's going to behave in their environment. So they want some measurements done. Of course, the bands below 6 gigs are almost used up, but that's, of course, where 5G will start off. Later on, I suspect it will move to millimeter waves. So we need higher data rates, we need a wider bandwidth, therefore we have to go up into higher carrier frequencies. The implications are, of course, that if you go to a higher carrier frequency, you have a smaller antenna. Also, unfortunately, we have a higher path loss, and could lead to lower coverage, which of course leads to more base stations. So that's something we need to look at. So the approach in any case is to increase antenna gain to compensate for path loss. Unfortunately, that means we lose peripheral vision. That means when you increase the antenna gain, you get a very narrow beam, can't see what's going out on the sides, etc. So you have to handle how you're going to deal with that. And then, of course, you know, some people are saying, well, maybe we can use massive MIMO to basically steer these beams around. Massive MIMO, I think, will be very expensive. We'll see. It might be something a bit different, but we'll see. So where are we going to put it? What we've got here is the frequency along the top, right? 6 gigs here, going up to you know, 70, 80 gigs there. And this is the region of the world, various regions. And the size of the blob is basically related to the number of fixed backhaul links operating at that frequency. So you can see India here has a huge number of backhaul links operating somewhere around about 15 gigs. And so maybe that's not a good place to put a radio access network. You can see, though, that there's some natural areas maybe where we could use spectrum for the radio access network. And, you know, those are the sort of areas that pop up. So somewhere around about 10, and then this is 26, up to 38 or something, and then right up here in E-band above 60, 70 or 80 even. Now, that's one thing. So that sort of tells you what sort of legacy users there are, right, that you have to deal with. But that's just in terms of microwave backhaul links. There's also other legacy users, such as satellite links, and they're also putting up a bit of a fight for the same spectrum. So I think we'll see how it eventuates. So when you go up into millimeter waves, you have to also take into account the loss going through the atmosphere. And you can see we have a number of resonances which cause the signal to have a very high attenuation. This is attenuation in dB per kilometer. All right. So, for instance, here's 10 dB a kilometer here. This band here, this is a 60 gigahertz band. And that's, of course, where the 60 gigahertz Wi-Fi 802.11ad is located. But there's also unlicensed bands here in the ISM, 24 gigahertz ISM band. They tend to put unlicensed bands wherever there's a high attenuation rate. Now that's the chart you look at if you're doing indoors. But millimeter wave is going to go outdoors as well, and so the cellular people in particular are interested in outdoors. And you'll see here that really this atmospheric loss is not the one to worry about. The one to worry about are these lines here, which is rain attenuation. And you can see that at 25 millimeters per hour, right, we have you know, going up towards 10 dB a kilometer extra loss. If you're having a point-to-point fixed link going over a few kilometers, this is clearly an issue. But for the radio access point, we're really looking at small cell sizes. And if you look at a sort of a cell size of 250 meters, which is probably what you get, you're going to have a 7 dB loss per kilometer, which is only 1.7 dB, 1.75 dB on the link. So you can actually handle that quite okay. Right, so as long as the range doesn't go up too far, hotspots and things like that should be okay. Now the ITU, the International Telecommunications Union, so that's the body that decides which parts of the spectrum are going to be used for what usage. And they had a meeting last year, and they decided that they would recommend the following bands for further study, right, for a decision in 2019. So that's what people are doing now. They're looking at these bands and they're going to see which ones are good. And of course, it's not only the cellular industry that's looking at these bands, it's also the incumbents, the people who are already there. They're basically also seeing what sort of interference they're going to have to put up with. So our university is taking measurements in these two bands. It's basically the limit of our equipment. So, but I think they'll be one of the early bands to be deployed. So what we do then is we have to generate channel model for each of these bands, and then we can pass it on to system designers who will then design the system. So why do we need a channel model? There are two reasons. One is in standardization, and the other is for planning and software tools for planning and deploying of networks. So if we look at standardization, standardization is basically a battle between big companies for IP, intellectual property, right? They're all trying to get their patents in there. And so they're all going to put up their own proposals, and then they'll have a big meeting and they'll decide which is best. And the way they're going to, one of the things they'll need to decide which is best is they're going to need a channel model which is consistent among all of them. So before the standardization process starts, the channel model must be fixed. Okay? And then they all use the same channel model to compare their systems. I've had experience in the 802.11 area, and of course what happened there is they have a subcommittee, they generate the channel model, and then they get the MATLAB code for that, and they give it to anybody who wants to use it in the standardization process. Okay, so we all got a copy of the channel model. We always told him which use cases we were going to use, and then we just put our algorithms through that to see how it behaves, right? So that's how it works. The other usage of a channel model, of course, is for planning software tools. So you know, you can plan a microwave link or a radio link. You just put in the heights and the conditions, and it will spit out the path loss that you expect to see. Now, channel models are split into scenarios. And in the 802 world, of course, you were talking about wireless LANs. You've got, you know, small office, large office, home, auditorium like this, courtyard, all that. So these are various use cases, and they would have a separate model for that. And in the cellular world, we've got indoor hotspot, urban micro, urban macro, rural macro, and various specialized add-ons. You can see there's a macro and a micro, and generally macro means the antennas are slightly above rooftop height, or the average rooftop height, and a micro means the antennas are below rooftop height, and basically you don't go as far. So there are two types of channel models. One is ray tracing, and the other is a statistical model. So the ray tracing model is used for path prediction mainly, and you have the signal and it hits an object and it bounces off. So you've got to know exactly the geography of where you are and the building structures all around you. So you've got to know that information. You've got to also know the reflection and transmission coefficients of the materials. And you've got to know the theoretical equations that govern these reflections and refractions. Okay, so that's the ray tracing model. Then there's a cluster base, which is a statistical model, where basically you see, this is your antenna here, and there's your mobile phone there. This is the base station, for instance. And you'll find that the signal comes into the base station from scatterers around the mobile, but also signal from the mobile that goes to another area of scatterers and then brings it in this way. So you have these clusters of scatterers all over the place. And what you want to know is the statistics of these clusters. So, for instance, the angle of arrival and departure. What statistical model will you use to choose this angle here, for instance? Also, the angular spread, which is the spread of the angle here. right? You have a statistical model for each one of those, and those statistical models come out of measurements. So a lot of people do measurements, generate the statistical model, then it goes into the computer, and then when they run it, they just put it through random number generators that will generate clusters at random, but with the same statistics. So this type of model is used for more like the standardization process, because when you do a standard, you have no idea exactly where it's going to be put, so you just use the statistics. All right, so these are all the information you need to feed into these models that has to come from, you know, channel measurements and people who are doing propagation measurements. This shows a statistical model for the path loss for a rural macro cell. You've got these, I mean, you don't have to look at the equation here, you just got to know that these straight lines come out of these equations. There's two, this is a line of sight line here, we've got distance against path loss, should be a straight line, and the slope of these lines and their offset is determined by a whole load of conditions here, such as antenna heights, ground conditions, and many other things like that. Okay, and then you get this particular line. Now, of course, you don't expect, if you're at a distance of 100 meters, you don't expect to get exactly that path loss, right? What you will get is that path loss with a log normal shadowing sort of like standard deviation of 8 dB. So basically, when you're going to choose a certain distance, then you generate this path loss here, which is like 110 dB, and then you add to it a random number generator with that standard deviation, and you'll get various values coming out. So that's the statistical part, right? So that's the rural channel model, valued up to 6 gigahertz. This is from the current IMT rural model. Thing is, it's not been tested above 6 gigahertz because there's no rural measurements being done, and so that's some of the work that we did to see if we could extend this model up until to the millimeter wave range. So basically the scope of our work is to do measurements in 24 to 40 gigahertz range. So this work really only started at the beginning of the year. We started from nothing, and we built the own equipment and then put it all together and started to do some measurements. So it's all at an early stage still. We were asked to do 3 types of measurements, which is a narrowband, path loss, and angle of arrival measurement. That's really good for the operators. That's really all they need. But we also have this sort of mid-band channel sounding, which is like, it's really looking at the impulse response of the channel. But we have a sort of a limited bandwidth of 100 megs, which is okay for today's systems, but it's on the low side for 5G. And then we have some wideband swept frequency measurements that we do from the network analyzer, and we can do that over short ranges, and we use it for looking at different materials, seeing what reflects and what doesn't, what transmits and what doesn't, and how much. We first start off with the antennas, which are just horn antennas. You can see they're very small. The smaller the antenna, then the broader the beam and the lower the gain. So this antenna here, right, has a gain of 25 dBi and a beam width of plus or minus 5 degrees. And that's similar to what you'd expect a massive MIMO antenna to have. So here's the equipment. You can see, I mean, it's just instruments basically connected to antennas, and then the mobiles, not very mobile, moving around on a trolley. And then we have this little robot here which scans in azimuth and in elevation, so we can see where the signals come from. The signals are quite directive, so we want to know where they come from, because that also has impact on antenna developments later on, for both the handheld and for the base station. So here's our campus. It's just off the screen here. You can see it there, and we're on a balcony there. And this was in the middle of the city, actually. And then we're going to do rural measurements in the middle of a city. Well, we can do that really because where you have a river here and a floodplain, and not allowed to build any houses on the floodplain, right? So it's full of sports grounds, and you can see at the far top right, this is a horse racing track over there, parks running through here, and then you know, ovals for various sports, you know, rugby, cricket, you know, soccer, all that sort of stuff. So it's sort of like a little rural area in the middle of a city. Now, what we are interested in, of course, is signals going through this tree depth area to see how much the trees are going to attenuate those signals, and also to see how far the signal will go. You can see this first point is a line of sight. There's no trees in the way for this one, and we have a signal to noise ratio of about 67 dB here, which is very strong. You go through the first line of trees and small bushes, it's down to 43, so you've already lost 24 dB gone. And then you go through the next load of trees and bushes, and you lost another 20 or so dB, you're down to 22 dB signal to noise ratio. Then you go further on, and as the range goes out, this beam slightly lifts. This is the terrain here. There's all the trees around this area. So as you go further out, this beam will start to lift, and so you'll clear the trees easier. And so you'll find actually that at this point we have the same signal to noise ratio as we did here. All right. So it's sort of recovered a bit. We then have a road crossing a bridge, and this is an embankment here. And on the other side of the embankment is a purely shadowed region. We cannot see this at all because of the built-up embankment on the road. And we're actually still getting a signal there. So we'll look at, what we'll do is we'll look next at these 2 points to see, you know, what's sort of happening. You'll notice that at the base station we have 2 balconies, one above the other, with 2 transmitters here, the high one and the low one. And what we want to do is see what sort of height gain you get. Right, the gain you get by going higher and higher at the base station. There's a height gain factor, and see if it's significant or whatever. And if you look at these signal to noise ratios, you see they change color. The red ones mean the red beam's stronger. Right, so you can see the lower beam is actually stronger, which is something that pops out in a lot of the measurements we're doing. The upper beam is stronger over here because it's in blue, and this is also the upper beam, and then we're back down on the low beam again. So you could in fact use this with called, you know, height diversity or something if you wanted to transmit. Always select the strongest beam. So we'll look at this point right at the far end of the coverage, about 1 kilometer away. And this is the polar plot of the signal strength you got. On this particular one is at 0 degree elevation, and this is with the antenna sticking up a bit, 10 degrees elevation. You can see the 0 degree elevation is best, and that's the azimuth. You can see the main beam is coming in here, And you can see there's also a reflection coming in from the other side of the river, coming down like that. So you've got, and also another little reflection here. So you could say you've got 3 clusters there, but this is the cluster excited by the high transmitter, and these clusters excited by the lower transmitter. So that's now what we're going to do is move the antenna to the other side of the road here, and we'll see what we get. So here we are. So we've come under the road and we've moved to here, and this is a big embankment that we have on our left-hand side. And we look at, when we have zero elevation on the antenna as it spans around, we'll find that we're in the noise floor. This is noise signal here. The whole thing's noise. Okay, so there's no signal coming in pretty much. But if we increase the elevation of the antenna, all of a sudden we see a signal coming in from this direction. And the direction is here. That signal is being reflected off a tower here, this pylon carrying these electricity pylons, or the electricity cables here. And this is being a reflector. And we find this a lot in our measurements, is that if you can get something high, which is, because it's high, it'll have a line of sight back to the base station. So the signal hitting that is quite strong, and then it will reflect or scatter in a region all around here, effectively filling in this black spot with signal. All right, so but what we need to be able to do here to get access to this is to have an antenna that can aim upwards. Right, we have to raise the antenna. So that's something I think the handset manufacturers or whatever might have to consider, like, can you move the beams around to grab signals that might not be coming from where you expect them to be. So tool objects can provide local coverage through scattering, both azimuth and elevation beam steering is required. This shows how you get the statistics. You each of the positions that we measured are plotted in terms of path loss and distance, or path gain and distance. You get these lines, so you get these scatter points. Those are all the points we measured. Right, there's the line of sight point here. And then we put on here, this is the model, puts these lines in. This is the line of sight model line. You can see it runs right through it. So that's a good one. It looks like the line of sight's going to be okay. This model is the lines for non-line of sight for different antenna heights. So on for the terminal side, I mean, basically our sights all have heights, should be, their reference point should be somewhere between those two lines. And you can see you get these things scattering around, and so you can have, now providing the distance between these lines is such that you can be within the 8 dB standard deviation requirement, then you can say that the model is holding. So what we find here is that the model is in fact holding up to at least at 24 gigs where we were doing the measurements. So that's the path loss model can now be extended from 6 gigahertz to 30 gigahertz for these rural environments. Then we looked at channel sounding. Channel sounding is where we're looking at the impulse response of a channel. And this is important more for the manufacturer of the equipment rather than the operator. Right, it's the delay spread over which the signals come in. So if you put out an impulse, the signals come in at all different times from different reflections. And it's that spread of signal that comes in that you have to equalize in your your receivers. The equalization is occurred like by having a cyclic prefix, which will cover that amount of delay. So for your OFDM, if you know about OFDM signals. So we can see here, this is our equipment, which was built up just using off-the-shelf components. We use these USRPs, which I think maybe you might have. A lot of people have now. Universal Software Radio Peripheral or something like that. GNU Radio, some people call them. And we have them with a sample rate of 200 megahertz. They have a bandwidth, RF bandwidth of 100 megahertz. So we're generating a low peak to average multi-tone sounding sequence and being transmitted and being received. And then it comes back here, and we can then receive those tones, and we can see what gain and phase they have. And from that, we can take the IFFT, and we get the impulse response of the channel. Looks like this. So this is the received signal. So you got these. We got like 256 tones here along there. You can see the distortion generated through the amplifiers. That's one of the features of OFDM. It does that sort of thing to amplifiers. These are these amplifiers were not linearized, so they do generate a bit of distortion. That's the received signal. This signal is the frequency response of the channel by measuring the amplitude and phase of all those tones, right? So you get the frequency response of the channel. Take the inverse Fourier transform, you get the impulse response. Then what we do is we threshold out about 20-25 dB below the peak of that signal here to get rid of any noise coming through, because the noise will also cause a peak. So this is the amplitude of the impulse that's coming in, and we have this is sorry, the second one is a blow-up version of that one. So the blow-up version basically shows the time range over which the signals are coming in. So that's a very sharp signal and has a sort of very low delay spread associated with it. Because it's in a test range, it's only going over a path of 1 meter or 2 meters, I think. And we've had to put attenuators in so it didn't overload the front end of the receiver. But then we do the real measurements. This is our campus. We put the antenna high here. So what we're trying to do is urban macro. That means high buildings, so you've got little squares and recreational areas and little roads going amongst it, generally high buildings and a higher antenna. So the antenna must be above the average height of the buildings. So for macro. The range of this cell would only be about 250 meters. But that's the sort of thing you'll get. So we're doing a whole load of measurements at these different red spots, and if we look at the measurement we get from here, looks like that. This is where we're plotting power received, that's the received power, against the angle, right? We're 360 degrees from 0 right back round to 0 again, or 360 there. And also we're looking at the RMS delay spread in the orange. So if we just go back to that signal, what's happening here when we did the measurements, we saw a lot of signal. This is a high building, so it's all non-line of sight. The signal was actually coming down through here and coming down this little corridor and then also bouncing off the back wall there or here and giving us a signal from both this direction and also 180 degrees behind the back wall coming in from behind us as well. And you can see the impulse responses are different at different places. Towards the peak of this impulse response, you'll see the signal strengths are low, so those amplitudes are low, but the time over which the signal is coming in is very high. When we go to where the signal is very strong, the axis changes, so you go from 0.02 to 0.3, over a gain of 10 there, so it's 20 dB increased signal strength. So here's the signal, and it's much narrower. And so the delay spread drops down. And then on the back wall, we have a sort of a fairly small signal, but also over a large delay spread, indicating basically each one of these will come from a different reflection, right? And therefore having a different time of flight, as you might say. So that's, we can plot power against delay spread, and you'll see some trends like strong signals generally have low delay spreads. Weak signals often also have low delay spreads. And medium signals seem to have a lot of delay spread. And then you have these isolated points with extremely high delay spread. So we're still trying to make sense out of those results. The third and final way of doing signals, measuring signals, is to use a network analyzer and sweep the frequency. This way we can measure how much loss, for instance, a signal incurs going through a brick wall or some material. So here's the transmit antenna, there's another antenna there, network analyzer here. And you can, if you sweep the frequency on the network analyzer, take the IFFT, you get the impulse response again, and you can see the reflections from the brick wall and also within the brick wall. So here is the brick wall. This is horn to horn with nothing in the way, right? Basically, this is free space, 1 meter free space. Generally, a single delta function, a bit of a skirt here caused by the low pass nature of the, the high pass nature of the waveguide. But when you go through the brick, you'll see that the position at 4 nanoseconds now changes to 5 nanoseconds, which means the speed of the radio wave inside the brick is a lot slower. In fact, it's going about half the speed of light when it's traveling through the brick. And also we see secondary reflections coming through due to cement air gaps because it's a double brick wall. So you can actually see what things are going on there as well. Yeah, we get somewhere around about a 20 dB loss going through a brick wall, or 19.6 in this case. We can also see the effect of going through glass. This is a glass here. And we're actually looking at the reflection now coming off the glass. So the reference basically gives you the black line. So it's a waveguide. So nothing happens until the waveguide passes the signal. It's a high pass filter. And then it should be fairly flat there. That's when you're going from horn to horn. Now, when you put a reflector here, you see you get you don't get as much coming back. So clearly, like a 10 dB loss, at least, reflection coming back from the glass. So there's not too much coming back. But you also get a deep null occurring at this frequency, and then another one occurring up here. So you take the Fourier transform, and you can see the impulse response now. And you can see there's a strong signal coming back, followed by a weaker signal coming back. And what's happening is that the signal is reflecting back. That's the strong signal. And then some is going through the glass and reflecting back off the second edge, or the other edge of the glass. And that comes back. And those two signals then interfere with each other. So at some frequency, they interfere and they enhance each other, so you get this zone. And at some frequencies, they interfere and the path difference causes them to be 180 degrees out of phase, and they cancel away from each other, causing this dips. And you'll get the same problem for the signal that goes on through as well. Right, you'll have two signals going through, and they will interfere with each other as well. And so you'll find that the glass changes its attenuation with frequency, but it's really not the glass that's doing it. It's in fact the multipath of the signals that are generated. I guess in Sweden, when you have triple glazing, this is going to be very interesting with lots of reflections. Okay. All right. So this, we did some literature research and basically showed, the literature research basically showed completely different answers for path loss in glass, and we think that most of it is due to this interference issue, which only shows with wideband measurements. You can only identify. You can't do it with narrowband measurements. There's some conclusions. I don't know, this is from other people's work and also our own, but you can see a brick wall, path losses between 14 and 28 dB. Lund University actually did the 14 dB. They have some bricks that are very good. They have holes in them. And because they got holes in them, they don't block the signal as much. I guess that's quite good for insulation. I guess that's why they did it. The big problem for millimeter waves is this. Concrete kills the signal, right? 88 dB of attenuation. We couldn't even measure it. And glass is sort of okay, but tinted glass is also not so good. I mean, it's in the same category as bricks, even worse. And plaster walls are not a problem generally. So if you're inside the building and you're just going through a plaster wall, then you can get to next door, the next room, okay. But getting into the building is going to be the issue. And that's why I think people are starting to look at this use of repeaters. If you can't get the signal in the building because it's made of concrete and it's got tinted glass in, then you're going to have to get the signal in some other way. So you put an antenna outside the building, you then put an amplifier, and then you put an antenna inside the building, and you repeat the signal in. And that's a repeater. So that might be necessary, I think, for millimeter waves. Added expense for the operators. Okay, so that's it, basically. We looked at 3 different schemes for measuring signal path loss and characteristics. Path loss measurements used by the operators, delay spread measurements used by the manufacturers, and also the wideband measurements to look at building penetration. The rural path loss model extended from 6 to 30 gigahertz. Tool objects. I think we notice this so often. Trees and man-made structures can locally scatter signal into dead zones, right? So if you don't have line of sight, but there's a high tree next to you, it'll scatter the signal down. And so it does improve the coverage beyond what you would normally think. Delay spread measurements, again, well, we just started here. Strong signals have a low delay spread. And the wideband measurements, we identify multipath components as the problem for, well, as one of the reasons that you get variable results in penetration loss through different materials. So high loss through some materials will force the use of repeaters in some buildings. So I will leave it at that. There's some references, and we acknowledge Telstra for funding the work, giving us peanuts to do the work, shall we say, and also supplying the frequencies, which is clearly nice to have, and Ericsson's for discussions and advice. So thank you. I think I was sort of asking me to extrapolate from the losses to cost. Is that correct? Of deployment, right? And I think basically our view is that the losses aren't as bad as what we thought they might be. All right. So maybe the deployment costs won't be as bad as we think they might be. But I still think that deployment, there's some technical issues to be solved in a deployment. And if you need to, you have to have, like, you need an extra 20 dB of gain somewhere in the system. Has to come from the antennas. They have to be basically beam steering, some sort of beam steering antennas. So that technical issue has to be solved, I think. All right. Whether the path loss is strong or weak, you're still going to have to do that, I think. Yeah. Well, the problem with the fifth generation, what they've done, they want to try and reuse the same channel models of the previous generations, right? Now, the fourth generation only went to 6 gigahertz. And so a lot of the work that's being done has been going from 6 to higher frequencies. And they've done it for all the common things, such as the urban micro schemes and the hotspots and all that sort of stuff. So that's all being covered, right? The problem is, to a certain extent, is they have two sets of models. They've got the millimeter wave model here. They've got the microwave model there. And where they join over, they're getting different results, right? You can sort of see how that happens, right? And so at somewhere around about 6 gigs is where they happen to join over. So they get a different result depending whether they're using the millimeter wave or the microwave, as you might say. Yeah, I think generally when we do models, we do them to cover what we need. And so I think the 4G guys covered what they needed, right? And now we go on to 5G, and now we have this problem with the two different models. But I think that's been resolved. I'm not sure how, but they're trying to tailor the models so that they gradually flow into each other. Yeah, it's... I mean, taking your question on further, you'd say, well, what should we be testing now for beyond 5G, right? And yeah, I'm not sure. We have to go even higher than millimeter waves. I guess that's what we have to do. Yeah. In millimeter waves, nothing's stationary, right? Like the slightest movement of the tree means that you've changed, you know, maybe even 180 degrees or something, phase shift. So what we find is that, yeah, the signal is always bouncing up and down. And so when you're doing path loss measurements, you have to average over a time period. And also, yeah, so when we do our path loss measurements, you know, you stop at a certain angle, you take a number of samples, and then you complete the span. And then we used to come back and then redo that angle again and take the samples, and then we would average. And so that's how we would do path loss. The delay spread, of course, is an OFDM tone, and we can cater the processing of that to handle any Doppler. What we're doing is that you have a comb of tones that you're transmitting continuously, and we would that waveform would repeat about 128 times. So if we have low Doppler, then we would average all that 128 and we get rid of the noise. But if we have high Doppler, then of course the channel changes over the time, and so we then have to average over shorter blocks, in which case we have not as good signal-noise ratio, but we're not affected by the Doppler. I think we can handle Dopplers up to vehicles that are like 40 or 50 or well, even I think 80 kilometers an hour, we can still handle it. But we haven't done that analysis yet. The data's there. I mean, you generate so much data in these measurements that you could be analyzing it for years afterwards, really. You might, if you could shine it straight down the railway track and it comes straight in, and the Doppler is then fixed, it's not spread. You've got a fixed frequency shift because of it. You might be able to handle that. The problem occurs is when you've got rays coming in from all directions and they all have a different frequency shift on. That's when you have real problems. But I think if it's just a straight frequency offset, then the signal processing can handle that. So yeah, so I'm not sure that answers the question, but I mean, if I was to do it, even if I was told I'd have to use millimeter waves to do this, I would be looking at doing something like that, like shining the beam straight down towards the train, oncoming train, right? And trying to keep the beam as narrow as possible. And as the train comes in, it'll see a strong signal, but it'll be a fixed Doppler shift, and it might be able to solve that issue. This frequency offset we can handle.
I would like to thank you again, and I would like to give you this little memory from this occasion. Thank you so much.
Not necessary.
Thank you.